Welcome to Hot Chips 2023. Session 3, Platforms.
So my name is Mark Hill. I work for Microsoft Azure, and I'm also emeritus at the University of Wisconsin. Today, this session is on platforms. I guess if CPUs are the engine only turns the drive shaft, and you got to have the platform to do the rest of the good work. And so we have 4 exciting talks from Intel, ARM, Intel, and Microsoft. The first talk, Architecting for Flexibility and Value with Future Intel Xeon Processors, is given by Chris Gianos. He's an Intel Fellow, lead Xeon CPU architecture and the data processor architecture team. Joined Intel in 2001 after 16 years with Digital Equipment Corporation, where he designed VAX and Alpha systems. Digital Equipment Corporation and VAX are 2 terms I haven't heard recently. Lives in Massachusetts, loves spending time with his new grandson. So, Chris.
Great. Thank you, Mark. I'm going to stick with the wandering mic, so you can keep that one off. Yes, I do. Thank you. Okay. Good afternoon, everybody. I can add Itanium to that list too after joining Intel as well. So it's been a long series of things. Good afternoon. Welcome. Thank you for your time. Hopefully, I can keep everybody awake after that lunch. I have sort of 2 goals today. I want to talk to you about our architecture that we're going to use in our next generation CPUs. And then I'll talk a lot about Granite Rapids, the CPU that we're going to build using that architecture. And I'm kind of separating these 2 out because I'd like you to pay attention to the architecture, because later today, Don Soltis, my partner in the processor architecture team, Don and I have been working together for over 20 years now. He's going to describe another processor that we're going to build and deliver using that same architecture. So pay attention to the overall architecture. I'm trying to describe how we get value and flexibility with it. And then you'll hear about these 2 processors that we're going to deliver. Okay, I'll start with a little bit of background about how we got where we are. This may not be all that surprising, but we took a spectrum of workloads and we started analyzing where do we think the world is going. We were looking for patterns. What do we want to do in our next generation? What's going to be interesting? What's going to be valuable? Where's the market going? And we decided to look at 2 sort of optimization vectors. One of them, core performance, of course. We're always interested in how core performance can optimize various workloads. And the other we started looking at a while back was density. And by density, we're using, I think, familiar terms to this audience: perf per watt, throughput per socket, those types of metrics. And then we started plotting these workloads out to figure out, which types of workloads behave to which types of optimizations, and where was the market going with these. What we generally found, looking at it, is that there wasn't a trend in one direction or another. It wasn't pointing us, you should move in this direction because this is what we see happening. It was like we were just seeing continued demand across the board. Workloads, EDA, HPC, scale-up databases, AI, even a lot of general purpose workloads continue to benefit from core performance. There's value in optimizing against that vector. If you look at the other dimension, the credible growth in microservices, cloud-native workloads, things like that, and they really do want optimizations. It's a real value to optimize for this metric that we call here density. And at the end of the day, I guess what I'm getting to here is we kind of concluded that we really need to deliver multiple products specifically optimized for some of these values. And there isn't just a one-size-fits-all model that we can adhere to. Okay, so we went back to, I guess as others have, our fundamental core architecture. I'm sticking a little bit with the core here. And we said, all right, we need to hit a couple of rather distinct optimization vectors. What can we do? And we looked at, let's try repipelining. There's process tuning that can be done. We did a lot of studies on various things like cache sizes, number of execution units, inclusion of specific functions. I'll take like our matrix engine as an example. And at least our conclusion in all of this is that, yes, through these kind of techniques, it's possible to move up and down within this domain. You'll get more value if you're trying to optimize for density or to get more performance for the core. But the range that we were able to achieve or that we thought was reasonable here wasn't to the level that we felt the market was really demanding. And if you think about it in this kind of graph, time moving up, even today we didn't think that we were getting enough out of that strategy, and it's only going to get worse in the future. So in short, we ended up biting the bullet and say, we are going to develop 2 core architectures, and we are going to optimize each of these architectures for a specific vector. We're going to develop what we're going to call a P-core, and I'll talk more about it today. It's the heart of Granite Rapids, the CPU that I'm sort of talking to the architecture by example with. We're going to optimize it for performance and analyze and look at the workloads in this compute-intensive AI space, a lot of general purpose workloads in here as well. And we're going to develop a second core architecture and product line based on efficiency. And Don will talk to you a lot more about that today. Now, before you think I'm going to spend a lot of time here talking about the differences between these two, and I'm not. I'm going to spend most of my time talking about the architecture in Granite Rapids, and Don will talk about the efficiency product. I do want to point out we were also incredibly concerned when we started down this path of ensuring that what we put together was easy and straightforward for our customers to adopt. We wanted to deliver a common platform, common ingredients, shared stacks, all the way up to the point of we expect with these optimized products, these range of products that we can deliver optimized across the spectrum, we expect to, you'd be able to walk up and literally just swap the CPUs and they will boot, right? These are not, separate and distinct things. They are complementary. Okay, so enough of the background. Let me sort of go into the details of what we're building. In this generation, this will be a multi-die architecture. I think lots of us have come to that conclusion that that's the right direction. Long gone are the days of monolithic, single die CPUs. In this generation, we're going to build, two distinct dies, an I/O die and a compute die. Somewhat common in the industry, maybe a little bit. In our case, the I/O die will hold our UPI fabric, the coherent, fabric that interconnects sockets, PCIe and CXL, and we're also going to put the accelerators that we embed into the product into the I/O die. Our compute die is where we'll put the cores, the caches, and the memory controllers. And we felt it was very important to couple all of these things together because that's one of the really good optimization vectors, independent of whether you're going for performance or density. That's a nice optimization vector. And then we're going to tie these dies together with this embedded multi-die interconnect bridge. And actually, I saw a demo out front that has a little bit more about it. But the EMIB infrastructure is a very high bandwidth, low latency, low power interconnect that we're really taking advantage of with this architecture. With this architecture, we wanted to build a modular system. And by modular, there's a couple of different areas that we're delivering modularity. We want to be able to enable using multiple dies within the socket. And I show, in this little cartoon on the right, I show 1, 2, 3 compute chiplets as options that we've got. And we've got 2 I/O chiplets, exact same chiplet. Another thing that you can see from this picture is that there's different structures behind the chiplet. The bottom right corner has more memory controllers than the other chiplets. Those little orange blocks are meant to represent memory channels. And it may be smaller or fewer cores or whatever, and then the other chiplets, we have a lot of flexibility in the structure that we can build with these chiplets. It'll all just interoperate, and it gives us one of those dimensions to optimize the products more specifically. And then, as you may be guessing at this point, we'll create chiplets that are E-cores and chiplets that are P-cores, and that's part of the way this architecture folds together. And then when we deliver this up into the platform, we expect, the same platform characteristics that we've had in the past. We'll, multi-socket support all the way from very rich 1-sockets, and I'll talk about our universal I/O a bit later, all the way up to 8-socket glueless, or we can still use controllers to extend above and beyond that. P-core and E-core products interchangeably within the same product. We will support a very large range of core counts in this infrastructure. The bottom corner die, consider that to be one of the smaller ones. We will have SKUs or products with this one that have single-digit core counts. There's still a demand for this kind of product today. If you go up to the larger ones, our larger chiplets that will stack multiple within the die, triple-digit core counts is what we'll deliver in here. So there's an incredible range of scalability that we expect from this platform. With our plans for these platforms, we're going to support up to 12 channels in this generation, DDR or MCR memory. If you're not familiar with MCR memory, I'll talk about it a little bit more. I think it's a really nice technology that we want to take advantage of. And then I talked a little bit, we'll use the advanced I/O characteristics that we're embedding into the I/O die to enable this range of platforms. We have gotten rid of the PCH for anybody who's curious. All of our platforms in the future, all of these processors are completely self-boot. Okay. Moving forward, before I get into the details of the individual chiplets that we're going to build, one of the attributes to look at here is this thing we call the modular mesh fabric. It allows us to create a logically monolithic mesh that crosses all of these die. And that, it means that you can any agent anywhere, an agent in the I/O die, an I/O agent, a core and a compute die, these things can interact directly over this logically monolithic mesh. The mesh ties together our slices into a unified shared last level cache. On Granite Rapids, our largest last level caches will go over 0.5 gigabyte. Very large last level cache. That's almost 5 times what we delivered on Sapphire Rapids. With these large shared caches, we still allow them to be segmented. In this generation, we'll allow subnuma clustering at the die level. And I really like the subnuma clustering in this kind of structure. These tiles, they're going to be large enough that the subnuma clusters don't suffer from fragmentation or stranded cores or things like that. But they're still nice and tight entities, so you get the affinity between the cores, the caches, and the memory system that's all integrated on the same die. In fact, we're going to make subnuma clustering our default mode in this generation. I think it's going to work out really well. As I mentioned, we use the EMIB technology to splice all of this stuff together and enable this super highway to exist between the dies. There's an EMIB interface, at the die boundaries between each of the die. Each one of those boundaries in Granite Rapids supports over 1 terabyte of bandwidth. It's a really massive superhighway that we can take advantage of to deliver the performance in the product. One other thing I'll mention, not necessarily related to the modular mesh, but the infrastructure we've built here, not only is it modular from the compute and the die perspective, the global infrastructure that we built is also modular and hierarchical now. So for instance, one of the global agents, our power management controls. We have a power management controller up in the top I/O die that manages power management for the entire socket. But each individual die now has a power management controller in it. They work together, sort of primary, secondary kind of relationships. But the individual die can manipulate their own power profile. They can change frequencies on their own. There's no need to stall at interfaces, coordinate across multiple dies. And this type of modular hierarchical interface exists across all of our globals. It's really nice. It aids to our ability to scale these things relatively easily and seamlessly. Okay, diving into the individual dies themselves. The compute die, very simple little structure. Basically, it's a matrix of tiles. I've outlined a couple of the tiles here. The blue tile is our compute tile. It contains the core. The core is private second level cache, and it contains this slice of the shared last level cache and the associated coherence logic that goes with it. The purple tile is our memory interface tile. We have the memory controllers and the IOs to the DDR. You can sort of compile as a parameter the number of rows and columns and the number of cores and the number of memory slices that you wish to have. And it's very, very flexible. There's sort of a third tile that I didn't blow up in this, and those are the little orange boxes that I'm showing here in the diagram. And that's kind of our die-to-die interface. We did make the mesh on the die at some low level modular, and then we use these die-to-die interfaces to egress a transaction, a packet, a data word off of one mesh, push it through the die-to-die interface over the EMIB, and then ingress it onto the next die. And that's basically it. That's the construction of the compute die. It's a very regular, a very straightforward system. Let me dive into the performance optimized core, the P-core now. This is a derivative of the core we're using in Sapphire Rapids. But we've taken it and we've pushed it forward 2 process generations, and then we went in and basically super optimized it for power efficiency. So our ability to scale with this core is much, much greater than process technology shifting alone would have enabled. We've significantly improved the scalability through the power efficiency. In addition, there's been a number of features, and I only highlighted a few of them on here. There's been a number of features added to improve the functional behavior optimized for performance of the core. I'll point out a couple. In the front end of the machine, we now have a 64K iCache. We've doubled the size of the iCache, improved the branch predictors, the misrecovery engine. The front end of the machine has been improved to better feed the back end of the machine. The execution units, FP16 support in the AMX unit, the matrix engine has been added. The floating point multiplier is now 3 cycles, and the back end of the machine supports significantly more outstanding requests, and it's better prefetchers, so we can also feed that end of the engine as well. So this core has been significantly optimized for performance. That was one of our primary goals going into this. I mentioned earlier this technology that we've been looking at that we really like and we're going to deploy here called Multiplex Combined Ranked DIMMs, or MCR DIMMs. They're addressing a problem that we've seen where there's a lot of workloads out there that can really benefit from bandwidth. And if you look at the story around DIMM bandwidth, DIMMs have not been delivering bandwidth at the rate we've been desiring to consume it. And we've been going out adding channels to sort of provide the extra capacity and bandwidth, but really to make up for some bandwidth in many cases in order to deliver what we need. And so we end up with the choice here at this point, saying, I want more bandwidth, I don't necessarily need more capacity, at least not in all situations, but I'm stuck. I don't want to pay for the expense and the capacity of DIMMs, but I really need more bandwidth to optimize the performance. And that's where these DIMMs come in place. It's a pretty straightforward technology. If you take a regular RDIMM and you remove the buffer, the registered buffer on the DIMM, and you replace it with a MUX, and then you optimize the path from the MUX to the CPU, you can improve the bandwidth of the channel. On Granite Rapids, we will drive this channel at 8,800 megatransfers per second, almost 40% faster than we can drive with conventional RDIMM technology today. The ranks behind the MUX get to run at half of that speed because the MUX is multiplexing them. So the ranks, the DIMMs, the DDR technology is actually still running at a relatively comfortable frequency. But we're getting the added 40% bandwidth out of running these things at the running the channel at the accelerated frequency. It's really nice in that these things are fully compatible at the platform level with registered DIMMs. So we don't have to make a choice of building a platform for these or a platform for something else. If you're using LPDDR or something like that, different platforms need to be built. We can build one platform and offer this as an optimization choice. They are being standardized into JEDEC. This isn't an Intel proprietary technology or anything, so they will be available. With the channels that we're providing, the 12 channels, and the bandwidth of these MCR DIMMs, we're delivering greater than 2.5x the bandwidth that the Sapphire Rapids platforms did. Significant scale up in bandwidth capability in this generation. And we've measured that in the lab today. Okay, another memory technology, talked about a little bit already today, that we've been embracing here is CXL attached memory. CXL, the link, obviously, offers us a low latency, high bandwidth, memory coherent interconnect. And so we're going to take advantage of that and attach CXL memory to the system. And we've worked very hard in this generation to make CXL memory what I call a first-class citizen. Everything that we want to do with memory, we make it independent of whether it's DDR attached or CXL attached. Same basically capabilities. It's a first-class memory system. If you attach CXL memory, you get the flexibility of added capacity and bandwidth to the extent that you need. We enable it being added in a couple of different ways. You can add CXL memory. It can form its own independent region, interleaved amongst the CXL memory components. In that case, as an independent region, software needs to handle targeting applications, or the applications themselves need to interact with a separate region. Alternatively, you can let the hardware interleave the CXL memory with the DDR DIMMs. In this case, you get a different latency bandwidth curve. You through CXL, you add bandwidth, but you also interleave the accesses between CXL memory and DDR memory. You get a different profile of latency. We've used CXL memory as having similar latency to, say, a remote access on another socket. You go off the socket, you go out over the link to another component, which it does a memory controller type read and write and brings the data back. Very similar types of characteristics. One new mode that we think is very interesting, we're somewhat excited about, is something we're calling flat memory mode. In flat memory mode, you configure the system, looks like my DRAM moved a little here. You configure the system with DRAM and CXL, 50% of each. And then you present this as one region to the operating system, just like you would with an interleaved system, and it's completely software transparent. But in flat memory mode, the hardware will manage at a cache line granularity the accesses, and it will keep the cache lines that are accessed most recently in the DRAM. And then for the lines that are not accessed as frequently, they get pushed to the CXL. So you can see how you get sort of the same type of behavior in many respects as a large region that's interleaved, but yet you get latency benefits because the lines that are important to you stay in the CXL memory. So we're really excited about this as an option, and we think it's another way that you can deliver performance. Okay, let me dive into the I/O die architecture a little bit. I mentioned we have universal I/O now. We have each I/O stack, and there's multiple of them on the I/O die, will support the UPI protocol, the PCIe protocol, or the CXL protocol. They can be configured, to do this. With UPI, we chose to make that link wider, but run it a little bit slower because we still want to preserve the ability to do, for a multi-socket system, a socket-to-socket, die-to-die link without involving repeaters. And for the trace lengths that we need in a lot of the multi-socket systems that we're seeing, that's the right choice. If you use the lanes for anything but UPI, then it's standard PCIe or CXL technology that runs at Gen 5 speeds. We've enabled this by 16 stack to be bifurcated. And you can choose the protocol at a certain granularity, and in our case, we chose by 8. So either at boot time or at hot plug time, you can basically select whether or not any 8 lanes, or the left 8 or the high 8 or the low 8 are PCIe or CXL protocol. And then from that point down, you can bifurcate further. And we support CXL bifurcated down to by 4 and PCIe bifurcated down to by 2, all at Gen 5 speeds. The I/O die has doubled the interface bandwidth to the accelerators. These are the same accelerators that you've seen on previous generation, but we doubled the interface bandwidth to the accelerators. That will speed up some of the accelerators, or for others, it enables more concurrent usages without bottlenecks. I also mentioned how we're trying to make CXL a first-class citizen. And on the I/O die, what we've done is we've extended our RDT technologies. If you're familiar with them, it's Resource Director Technologies, quality of service capabilities that let you monitor and control cache allocation and usage, or memory bandwidth allocation. We've enabled I/O channels to be treated a lot like we currently treat processor threads. And you can now monitor and control the bandwidth and the cache allocation of the I/O channels, much like we were doing with processor threads. All links can be encrypted, so you have full security capabilities on the interconnects as well. Let me move on. I'm not going to show a lot of performance information here. This was a choice Intel made. There will be disclosures coming up in the next month at a session we call Innovations, where there will be a lot more detail presented around configurations and workload behavior and performance and that type of stuff. But my AI team has been out there looking really heavily at some workloads, and they're really excited about these. They've been looking at what they call mixed AI workloads. Workloads like speech recognition, recommendation engines, video processing, video creation. Look what Adobe can do right now. You literally make up images with some of this technology. And they've been looking at how these behave. And what they're seeing on Granite Rapids is the combination of the significantly improved memory bandwidth characteristics, the scalability up to much higher core counts, and the super large last level cache that we have, as well as all of the enhancements that we put into the core itself, we're seeing 2 to 3x the performance on a lot of these types of mixed workloads even today. And that can translate into, you have a better capacity for workloads. Your AI types of workloads like large language models just have capacities for more parameters and things like that. It's a really exciting result, and we will be getting and showing you more performance results for that soon. Okay, so let me wrap it up a little bit here. Hopefully with all of this, you've seen how the architecture that we defined is going to deliver to these multiple optimized products. That was one of our goals. We're going to do it within a common platform infrastructure, firmware, software stack. It'll all be totally complementary. It'll all be common. You've seen now too how Granite Rapids is the P-Core performance optimized solution that we're going to deliver. And you see how we're trying to optimize it for performance. It's delivering the bandwidth, it's delivering the scalability that we were looking for. We've added CXL memory and features like that to further expand the scalability and the performance of this solution. Basically, we're hitting the optimization targets that I described in the beginning, and this will be the most performance Xeon processor we've ever delivered. Thank you. Questions?
Do we have a Slack question first, or should I ask a question?
We have a couple of questions on Slack.
Sure. Fire away.
So the first question is from Pavan Goti Am. What degree of separation or synergy exists between workloads reflecting scale-up and scale-out markets? Do you see them being very disjoint in the future?
The workloads themselves is the question. I mean, so let me answer it from the perspective of the products that I think we're going to deliver. We see a lot of overlap, right? I mean, just because we've optimized these things towards different points, right? These are both Xeon processors with all, very much common capabilities in many respects. And we see an awful lot of overlap. That's what those pictures I was trying to show in the beginning when I showed two different processors, as an optimization target. There's a lot of overlap in the middle, and it's an entire spectrum. And so we're going to exploit that. We feel that either processor can be a good choice, but we're going to provide sort of better choices in certain vectors for certain workloads.
Thanks.
All right, let's go here. Name, institution, and no questions about future product plans.
Hi, Alan Cancel with Nailsway. Just a point of clarification, on your I/O die architecture, you're showing 16 lanes of PCI stroke CXL, but on the Ayer Labs demo, I got the impression it was like 2 channels of 6 or 4 channels of by 8 lanes of PCI. So if you're familiar with the Ayer Labs photonic demo outside,
I'm not following the question.
well, it looks like the Ayer Labs demo looks like you've got twice the bandwidth of what this slide says on an I/O tile.
Okay, let me follow up with you on that one offline. I think you'll have to show me what you think you're seeing. I do have, by the way, just in case anybody's interested, I have a Granite Rapids sitting up here. If you haven't seen a server CPU in a long time, it's amazing. They have changed since I was younger. And I was younger a long time ago.
All right, go.
George Kozma, Chips and Cheese. I was looking through some of your slides that you released to the press, and I noticed that you guys were talking about how you could write interoperable programs between Granite Rapids and Sapphire Forest. However, does that imply that Sapphire Forest also has AVX10? Because otherwise, you're limited to AVX2 and yes.
So the product term that Don will talk about later is Sierra Forest. Sapphire Rapids was the previous generation. On Granite Rapids, we are going to support what I think has been published as AVX 10.1, which is basically AVX 512, but the CPU ID and other information in AVX 10 that allows you to basically program to the AVX 10 specification will be enabled. But we won't get in Granite Rapids the 256-bit instruction instructions that come with AVX 10.
Will Sapphire Rapids have that? Sierra Forest.
Sierra Forest. I will let you ask Don about exactly what Sierra Forest will have.
Okay, thank you.
Okay, Slack.
Yeah. Question from Cliff Young, Google. Do you have a rule of thumb for how to think about P-core versus E-core performance and energy consumption? Like, is a P-core 1.5x the performance at 2x the power?
I don't have a good metric for you. Don has some information, actually. I think it might be good to look at his graph and try to interpret that, because I believe it's very workload dependent in many respects. And so how you want to compare a couple of points, but I'll defer you to a graph that Don has in his slide that he will present later today that gives a relationship between how we see the behavior against, say, the efficiency spectrum and the performance spectrum for the two products. And I think that will probably answer the question very nicely.
I have one more related question. Could you make a package with E-core compute chiplet and P-core compute chiplet? Would that also just work with one unified stack?
So architecturally, probably. Our intention is to not mix E-core and P-core within the socket. We think the better choice is to configure the data center based on the data center needs to have the appropriate ratio of P-cores and E-cores. I don't think you want us sort of predefining what the right ratios should be. And there's complexity in that. And at least from our server data center analysis, and especially for this first generation, we intend to provide E-cores and P-cores, and then buy the appropriate number of sockets to get the right ratio.
Thank you.
We have one more very succinct question.
Hi, Curtis McAllister, Elian. I had a question about the flat memory model. So where's the location information stored, and how much does it take away from your total effective memory capacity?
It's part of the storage in the DRAM. It takes up 1 bit. That's one of the reasons why we went with the 50-50 mode. It's either here or there, and that bit tells us where it is. Okay. So when you're running flat memory mode, the ECC mechanism used on Granite Rapids is 125 bits worth of ECC. It is imperceptibly different. We've got a bunch of data on that if anybody wants to see it, from full 128.
Okay, with that, we'll have to leave it there. Thank you.
Thank you.
Our next talk is CSS-Genesis, ARM's Neoverse N2 platform. We heard about the processor earlier. Delivered to partners as fully verified customized compute system. The speaker is Anitha Kona. She's a lead system architect and fellow at ARM. She's been at ARM 9 years working on future technologies and the architecture of infrastructure systems. So without further ado, Anitha.
Thank you, Mark. Good afternoon and hello everyone. My name is Anitha Kona. I'm the lead system architect and fellow at ARM, based in Austin, Texas. Today I'll be covering ARM Neoverse N2 compute subsystem, called as CSS-N2 or CSS-Genesis. It enables our partners build and deploy industry-leading ARM PPA in record time. Why CSS? The industry is facing 3 major pressures. We are seeing significant increase in development cost with every advanced node. And here it shows the report from IBS. The cost is broken down into software cost and hardware costs associated with the development of these SoCs. For the software cost, our partners can leverage vast software ecosystem out there that work on ARM. But the hardware cost, which is associated with the design and IP validation, is growing significantly. Next, as the designs are getting bigger and more complex, it's becoming harder to get highly skilled design talent to design these complex systems, in order to maintain a reasonable time to market for the new products. As the Moore's law is slowing down, the need for specialized silicon is not slowing down. We are at 5G today with 120 zettabytes of data being generated. The need for data compute is only increasing. So ARM CSS-N2 is kind of addressing some of these problems. Sorry. is going to address all of these problems. ARM supports different paths to silicon with varying levels of cost, risk, and specialization. You can see on the x-axis, you see the differentiation and customization, and the y-axis, the cost and the risk associated with the product development. Here it shows where the CSS option fits into the spectrum of choices. At the very left, you can pick up off-the-shelf ARM-based SoC from a silicon partner. That would allow them for a very quick and cost-effective way of deployment. However, there is no differentiation provided or customization available at the SoC level. At the extreme other end, we have our architectural licenses. A partner going down this path has full flexibility to differentiate and customize, but that comes with a very steep cost. And it's very challenging to build these system IPs, cores, ground up, and customize them, and require a world-class team and a very long years to develop. That sweet spot today is the IP model where our partners take our CPUs, interconnect, and system IPs to build their SoCs. It provides flexibility for customization, but even that is considerable effort to come up with the system architecture, IP validation, and fine-tune performance. CSS, the new validated CSS, is to accelerate and develop on that IP portfolio and enable the partners to build at a low cost and time to market. CSS product is the fastest path to production silicon, world-leading performance, and on a leading-edge technology. In order to achieve this, we have to focus on more than just underlining ARM IP. CSS N2 is a multi-core subsystem product. ARM develops, fully validates it, optimized, fine-tuned for performance, and we ship this pre-tuned RTL to our customers. We use these platforms to develop new technologies that cut across the traditional IP boundaries, like the CXL memory expansion. We enable partners to attach on-chip and off-chip accelerators for differentiation. CSS also supports chiplet-based design, where partners can put together, connect multiple chiplets in a chiplet multi-chip fashion. Along with the RTL, we also develop implementation package to enable partners to hit their power and frequency targets. And CSS also comes with a reference software stack with the system ready. Neoverse N2 with N2 core as efficient performance. It can span across from scale-out cloud, networking, and all the way into 5G applications. With its very strong performance and efficiency, it can be deployed into different market space. CSS N2, being configurable compute subsystem, can enable partners to build SoC to span across these markets. With multi-chip capability, you can scale to 128 to 256 cores to go into cloud data center applications. And also to a small optimized compute up to 64 cores for the edge 5G applications. Diving down into technical details of CSS N2. It is a configurable subsystem, as I mentioned, with max 64 cores per chiplet. Can be configured to 24, 32, 62 cores to go into different market spaces. The max core target frequency achieved is 3.6 gigahertz in a 5 nanometer process. Other configurable options are, you can size the cache sizes, can be changed according to the partner needs. The core private L2 cache can be sized up to 1 meg, and also the SLC system level cache can be configured up to 64 megabytes. CSS provides standard CHI interfaces, up to 8 interfaces, so the partners can connect to their DDR and LPDDR memory controllers. provides standard HC interfaces with full I/O virtualization support to connect to Gen 5 PCIe controllers or as partners specialized on chip accelerators. And it also comes with CXS interfaces for connecting to CXL devices or multi-chip support over UCIe or CXL PHY to support multi-chip architecture. CSS also includes system management logic, the SCP, MCP, along with the firmware, reference firmware. Here it shows a very high-level CSS block diagram, where all the cores and the system IP are stitched together, fully verified and fine-tuned for delivering optimal performance. All of the AMBA standard expansion interfaces connecting to memory controllers and the PCI controllers and to the rest of the SoC are fully validated. CSS is designed and validated to be system ready. What is system ready? System ready is an ARM compliance program based on our system architectures, base system architecture, server-based system architecture, SBSA, and server-based root requirement specifications. With this compliance, partners can be confident that generic off-the-shelf OS will boot out of the box on their devices. CSS is optimized for performance and fine-tuned for PPA by running various standard server benchmarks like SpecEnt, Nginx, MySQL, and other, etc. Implementation guidance is also provided how to put together these complex and build these big compute subsystems and to achieve target frequencies. Diving down into individual blocks. Processor block, it contains N2 core plus all other glue logic needed for interrupt support, power management, clocking, and debug. Neoverse N2 core is ARM's first infrastructure ARM v9 implementation. N2 core supports advanced features like SVE vector extensions with new ML instructions, memory partitioning and monitoring, MPAM, per thread resource allocation, enhanced cryptographic instructions. It also supports advanced power and performance features. MPMM, which is the max power mitigation mechanism, dispatch throttling to improve overall system power efficiency. This also provides interface logic for partners to add system control framework to add their specific partner-specific sensors. System control and management control processors. Both SCP and MCP are based on ARM Cortex M7 core. It also includes other needed logic, logic timers, watchdog, message channels for core-to-core communication support. SCP is trusted and it manages all the system-level control like power, voltage management, clocking, and resets. It also handles per core DVFS requests from all the AP cores. MCP is the satellite controller that communicates with the external baseband management controller. It handles on-chip management, logging various events like RAS events, communication alerts, out-of-band telemetry collection, and communicating back to the external BMC. System MMU and interrupt controller. MMU 700 is compliant with SMMU architecture 3.2. All the I/O interfaces are integrated with SMMU to provide address translation and virtualization support. MMU 700 supports single and two-stage translations on these interfaces. It supports advanced V9, ARM v9, v8.4 features like MPAM, secure EL2 and TLB range invalidations. Generic interrupt controllers. GIG 700 is compliant with the GIG architecture version 4.1. It handles all the interrupts from all the peripherals that are part of the CSS and also core-to-core interrupts within the CSS. It also provides expansion interrupt interface for partners to connect the interrupts from the peripherals that are added outside the CSS. System interconnect. The main system interconnect that connects all the cores and the system components in a coherent way is ARM Neoverse CMN700. It is a mesh-based cache coherent interconnect. CSS-N2 has a 10 by 6 mesh and runs at 2 gigahertz. Mesh as distributed system-level cache shared across all the cores and the I/O devices. Supports advanced AMBA features like atomics, stashing, and RAS features. Support system cache groups for affinity and isolation, improving the mesh bandwidth utilization. Mesh as a cache coherent gateway to connect multiple chiplets in a fully coherent multi-chip fashion. I'll cover CCG a little bit more in the next slides. Accelerator attach. CSS-N2 provides I/O interfaces to connect to partner-specific specialized differentiating on-chip accelerators, or PCIe controllers for external devices. These interfaces support up to 64 gigabytes of bandwidth in each direction, or PCIe Gen 5 bandwidths. It supports bifurcation up to by 4 devices for PCIe. Core scaling. As you have seen today, everybody is emphasizing on the need for compute-intensive applications that are pushing for higher core count. Partners are asking for scaling up cores. CSS-N2 allows to scale up to 256 cores by connecting multiple chiplets to deliver more performance in a fully coherent fashion. You can connect up to 2 chiplets within a package or 2 sockets together. CCG Gateway provides ability to connect 2 dies within a package through UCIe, a standard UCIe PHY, or a partner-specific die-to-die PHY. It also allows 2 sockets to connect through a standard CXL PHY. SMP protocol is used over both chip-to-chip and socket-to-socket links. CSS-N2 supports multiple interfaces needed for multi-chip support. As mentioned before, SMP interfaces for coherent accesses, serial interfaces for communication between control processors, SCP and MCP, for synchronization during boot time. Core side cross-trigger interfaces for ability to trigger any cores on all of the chiplets. And timer synchronization interfaces for balancing the system counter on all the chiplets required to provide same timestamp value for all the cores. CCG, Cache Coherent Gateway for SMP connections. On the left, you can see CCG is integrated with a UCI controller for chip-to-chip communication, or UCI PHY. CCG implements most of the SMP protocol layer. A thin lower link layer is implemented as part of the UCIe controller. And on the right, you can see the same CCG can be integrated with the PCIe CXL controller for socket-to-socket communication. Lower link layer is implemented in the CXL controller in this case. Most of the third-party vendors are implementing this lower link layer in their controllers that our customers can use. CCG connects to these controllers through a standard AMBA CXS interfaces. As the new advanced technologies are emerging, CSS-N2 allows partners to adopt industry-standard I/O capability quickly. CSS allows partners to expand memory capacity through CXL 1.1 Type 3 devices, supports connecting high-speed PCIe Gen 5 accelerators and external devices. CSS comes with fully validated I/O interfaces. We have integrated third-party control CXL and PCIe controllers to validate these I/Os so that the partner is ready to integrate any third-party IP and get going. Same CCG supports both SMP and CXL protocols. Can choose between SMP or CXL through software at boot time. Here it shows CCG connecting to CXL controller. CSS-N2 can be connected to any third-party offered CXL controller to connect to CXL Type 3 devices. Another deliverable of CSS is the implementation guideline. This is to enable partners as a reference to make sure that big systems can be physically implementable and achieve target frequencies and guide our partners with physical implementation challenges. Here you can see 64-core CSS implementation in 5 nanometer process. The compute part of the chip is tile structure laid out in a tile fashion. Each tile has a dual N2 core and 2 HNF slices. And the tile is stamped multiple times to form the compute part of the CSS. Here you can see a reference to SoC floor plan with estimated dimensions of the PCIe PHY and DDR PHYs and other system components provided as an example guidance for the partners. ARM builds physical IP, standard cell libraries, fast cache instances optimized for CSS. N2 POP implementation is optimized PPA for core and mesh configurations, metal stack, floor plan, EDA flow, and sign-off. Also included with the CSS is the reference flow scripts, physical IP, and documentation. It also comes with HNF, FCI packages optimized for PPA. CSS-N2 includes reference software, which is the key component for partner to deploy an SoC. So it comes with a reference software along with a fixed virtual platform model of the system. It is designed to help partners with bootstrapping engineering software development. Comes with RTL for smaller configuration for FPGA build for partners to develop their software. Reference software integrates multiple components, SCP, MCP firmware, AP trusted firmware, etc. It also includes software features like boot flow, security and power management, and RAS as a reference. It is upstreamed for partners to download. To summarize, going back to the challenges introduced at the beginning, there is an incredible need for more efficient computing across all infrastructure workloads. And the only near-term solution to get there is through building specialized silicon. We developed Neoverse CSS to deliver a fully validated and performance-optimized compute subsystem that our partners can use as foundation for their own specialized silicon development. CSS offers interfaces to integrate customized accelerators for differentiation, I/O memory on top of our IP foundation. And the benefits of CSS to customers are real and significant. CSS helps improve time to market. We have had one partner progress from design idea to working silicon in just 13 months. CSS helps reduce cost. We have had another partner telling us that CSS has saved 80 engineering years. And then they can use this saved years for their customized silicon for differentiation. CSS-N2 is the first generation of Neoverse CSS products, but it built upon decades of time developed on reference designs and software ecosystem, and so that it leveraging decades of platform and software ecosystem, improving the ARM's first platform to infrastructure. Thank you, everyone.
You can stay there. All right, so we're ready for questions. Why don't we start with the Slack channel since it takes people a little time to move to the microphone.
Question from Christoph Novak, Moore's Law is dead. He has two questions. The first question is, are all cache configurations, mesh sizes proven in silicon, or are only specific reference configurations proven in silicon? That's the first question. The second question is, on slide 4, power control is part of partner innovation, but later in slide 9, you say that CSS includes system and power control. Does CSS always have this power control, and how would partners' own power control interact with the CSS power control? Thank you.
So on the first one, the CSS-N2 subsystem we offer is proven in silicon. One of the partner has been testing it in silicon right now. The second one about the power management, we provide the SCP, the system control processor, which manages all the DVFS for the cores, resets and clocking. But we expect the partner to add the sensor logic, like the thermal sensors, adaptive clocking, PLLs and all. So those, we provide an interfaces to add for those components.
Thank you.
Another Slack question?
Yeah. This question is from Amarveer Chana, Cambridge University. From the previous Neoverse N2 talk, it was mentioned CNM 700 can support a heterogeneous hub and spoke model. Are there any CSS offerings with this multi-die topology?
I cannot comment on that at this time. Okay. So it does support CMN. CMN does support hub and spoke, but I cannot comment on the roadmap of that.
Thank you.
Hey, this is Sumit from Google. I had a question as to how do you deliver the CSS to the partners? Is it like some scripting environment where the partner can play around with the different options, or is it more like we tell you the configuration or work with you and we get a bundle which has the RTL and the UPF and everything already in there?
So CSS is delivered with some scripts and RTL, but there is some configurable opportunity, but not fully configurable. As I mentioned, you can configure the number of cores to 24, 32, or 64, and also you can configure the cache sizes according to the needs. But the mesh size remains 10 by 6.
So that configuration is on the partner side then?
Yeah.
Okay.
Yeah.
Thank you.
Yeah. A question from Ravi Chandran, Intel. Can you comment on performance scaling challenges with core count with CSS?
Sorry, could you repeat?
Can you comment on the performance scaling challenges with core count with CSS?
So as the core count increases, your memory bandwidth per core also increases. So it doesn't scale linearly, right? So it kind of scales as the bandwidth per core decreases. So there is bandwidth requirement as it reduces because of the core going up. But CSS is designed to support optimally until 256 cores.
Okay, thank you.
There's another question?
This question is from Grace Luo, University of Wisconsin-Madison. Do you envision a memory translation or isolation hardware function in front of the GIC? How does the VMs communicate with the GIC if the GIC operates in the system physical address space instead of virtual address?
For the gig, you're saying?
Do you want me to repeat the question?
Yeah.
Yeah. So the question is, do you envision a memory translation or isolation hardware function in front of the GIC? How does the VMs communicate with the GIC if the GIC operates in the system physical address space instead of the virtual address?
So there's no isolate logic needed in front of the gig. Gig supports virtual injection of the interrupts. So that's how it handles the virtualization.
Okay, thank you.
I'll ask a question. So how do you think the data center market is changing the needs that we have to have from ARM?
Sorry. Mark, could you repeat?
So there's this market for cloud data centers, for example. How does that affect what ARM believes is necessary in their technical roadmap?
So I think as the need for the data and the compute is increasing, partners, there is a need for the specialized silicon to support this the need for the data increase in the compute. So ARM is helping partners to develop these SoCs so that they can build upon CSS N2 and work on their specialized and customized acceleration.
Final question?
Yeah, no, we don't have any more
Okay.
questions.
Let's thank the speaker. Okay. All right. Our third talk is on Intel Energy Efficient Architecture with Efraim Rotem. He's an Intel Fellow, Lead Power Performance Architect in Client Systems Architecture Group. He's been with Intel since 1995. Started as a test engineer, became a power architect, and he's got a PhD from Technion, which, let's see what I want to say here. The Technion is the, MIT is the Technion of the United States, right?
Okay. Thank you, Mark. So, Intel's mission to create world-changing technology to improve the life of every person on the planet implies the human factor. And this human factor will be the topic of my presentation today. I will show how we build systems that matter for the user and how we should look and evaluate them. What matters to the user basically is performance and energy. Performance can take many forms. Throughput performance, meaning taking a big computational task, running to completion and get it done in a quick time. For the client system, which is my focus today, we care very much about responsiveness. When we interact with the computer, we want an immediate action and we don't want to wait too much. This is true for existing workloads, and this is also true for emerging workloads, AI and so on, that will meet our products few years down the road when the products are already shipping. Energy matters for the user as when it comes to system design and ergonomics, how thick the system is, how heavy, fan noise, heat, and so on, and full day energy consumption, which translates into battery life and carbon footprint. And those two are obviously dependent on each other: performance, cost, energy. I'm talking energy. Often you hear about power efficiency, and so on. Power in this context is usually talked on average over some window of time. Without going into the details of the technology, I will use them interchangeably as needed. So the rest of my talk will first describe the features that we are putting into our product. We are launching in the coming 2 months our new client generations. I'm describing some of the features and measurements without going into product disclosure. For the details, you will need to wait a couple of months. I will show how we figure out what, in the context of a client, what the user needs, when he needs it, how we spend the energy to deliver great user experience, and how we conserve energy the rest of the time. The second part of the talk would be how we measure the value of these technologies, and as important, how not to measure. I will start diving into the technology. The fundamental of power and energy management is DVFS, dynamic voltage and frequency scaling. Changing voltage and frequency increases the power and consumes more energy. The hybrid architecture further increases this dynamic range. The question is, in power management or energy management, is how we figure out what is the right frequency to run it. The fundamental, which is on the existing product and has become an industry standard, is demand-based. We track the utilization of the computer. If there is a demand for more compute, we increase the frequency, and vice versa. This does a pretty good job in addressing throughput performance, but when it comes to client responsiveness, it is often slow to respond. So the first algorithm that was already in our products that has been upgraded on the product that are coming out is the Intel Speed Step technology. I focus here on one piece of the user trace or user work. This is where a user clicked on a mouse and opened a document. And we can see that from an idle state, the system transitioned to a high utilization. So we, in the power management controllers and our system, we track the telemetry and we implement a fast transient to high frequency. Obviously, there are trade-offs between false positives and false negatives. If we get too aggressive on ramping up, we may lose energy, and if we get too slow, we might lose some of the transients. So this is a continuous improvement, and what I show here is a measurement on our latest and greatest system. In blue, it is performance, and in orange, it is the energy. The left set of bars is the responsiveness, the short burst workloads, and the right side are the more sustained and throughput performance. And we see that on the responsiveness kind of workloads, we are able to deliver up to 35% more responsiveness to a user-initiated action. And at the same time, by the fact that we finish and go faster into a low power state, we are also able to save energy, up to 15% energy in this case. There is so much we can do with microarchitectural power management, tracing, and optimization. Lucky, we, the human, observe patterns of behavior. If we browse the internet, we will browse it for a while. If we are editing a document, it is never one click of a keyboard or a mouse. And machine learning and AI are very good in extracting user patterns or patterns in general. So what we have done, we have added a machine learning algorithm that collects information, microarchitectural behavior, together with information that comes from Intel Thread Director and speed shift technology, and generates a prediction of what the user does right now, what is the overall action, and tunes the power and energy and performance accordingly. So this is how the prediction works. The orange line is power consumed by the CPU as an indicative of the amount of work that is being done. The x-axis with the black marking is this set of applications that are running. These are real user applications, somewhat condensed into a shorter time, but these are the kind of things that the user does over the day. The green line is the data, a sample of data that is coming from Intel Thread Director and the speed shift technology. This is information that tells us whether the thread is foreground or background, what is the priority of it, and so on. So we compile all these, throw them into the AI algorithm, and we generate the blue curve, which is the classification of the workload. What is the workload? This is a semanticless value. It is a mnemonic value that just tags the kind of workload, and we see there idle, fixed quality of service, sustained workload, bursty, and so on. And based on this generation of tags, we are adjusting the power and performance characteristic. Let's focus on the same burst that I showed earlier. This is opening a document and start editing. If we look only on the activity, we see that we were idle, we jumped to high activity, and that's it. If we look at the blue line, we show more refinement of detecting the behavior. At the beginning of right after the click, there is a tagging of low quality of service, meaning there is some I/O happening in the background. The CPU doesn't matter much until the data gets to the CPU. And there is a burst of high utilization when the software opens the file, decompresses if it is compressed, security, arranges all the metadata and the data, and then starts the user activity, clicking the mouse and so on. So this is a low quality of service, and then closing the document, another burst of high performance. So with the refinement of the machine learning, we are able to know exactly when the high performance for the processor is needed, give the energy budget at that point in time, and save it the rest of the time. So here I compare the machine learning driven power trace to a static setting. I picked a static setting which is equivalent in performance. So the two lines will be aligned, and you could see the picture. And we were able to save between 10 to 20% energy over the entire run. 10 to 20 depending on the phase of the execution. So this is the set of features that are intended to budget correctly the energy consumption based on the user activity. How do we measure it? We have the industry standard benchmarks that are a powerful tool to assess raw performance. We acknowledge and we optimize the systems, and we are going after a high uncompromised performance, but there is a general agreement that energy consumption is highly important. Today on this stage, almost every presentation mentioned the need for power efficiency, energy efficiency, and so on. And a metric that was very often used again on this stage was performance per watt. So first, what does performance per watt mean? You take a benchmark, heavy benchmark of your choice or that serves you best, and you run it on the computer until completion. You measure the average power consumed over this run, and you generate a benchmark score, which is inverse proportional to the runtime, and you divide by the two, and you get some number. This is not a new metric. This is metric that basically was invented in 1964, that called PDP, power delay product. And it is heavily used in the industry. I mean, today on the stage I heard 5 or 6 times people mentioned performance per watt. Is it still meaningful 50 years after it has been conceived? 50 years of power management technology and energy efficient technology. After all, it has performance in it, it has watt in it, so it somehow implies that it incorporates performance and power. Well, not really. And let me be a little geek and throw in an equation. I know that I risk losing some of the audience by putting an equation, but try to stay with me and follow the math, and I'll show you a magic, and I'll show you how I make things disappear. Performance is, as I said, inverse proportional to runtime. So the units are 1/second. So if you take 1/second divided by power, you get 1/Watt-second. Watt-second is joules or energy. So you started with a metric that says performance per watt, and you added up with no performance in the metric. So now comes the part that I go to the other virtual side of the stage and show you where the performance rabbit is hiding. And it is hiding here. What the orange and the light blue lines are the spec int running on our latest and greatest processor at different DVFS point, at different voltage and frequency points. And I plotted here the performance per watt as a function of performance, as indicated by frequency. And what we see is that the highest performance per watt point is almost at the lowest performance. And as you increase performance, the performance per watt goes down. So pick a number, any number, and you can meet the performance per watt. So it is not really indicative of energy efficiency. It's an arbitrary number of your choice. The point in which we measure the performance per watt normally is way down this curve, around the 30 or 40% of the most energy efficient. I'll get back to the dark blue line in a second. So basically, no surprise, this is DVFS in action. You lower voltage frequency, you lose performance, you save energy faster, and so on. So it's not only an arbitrary number, it is misleading number. In what sense it is misleading? I show here product A and product B. This is not by all means a competitive analysis. It's not meant to show any real product, just an illustrative. So there is product A and product B. Product A runs at delivers lower energy on each and every performance point that you see. So definitely it is more energy efficient. But out of the box are the 2 points which are highlighted in big bold dots, and this is the frequency that they are chosen to be tested. And you may see in the tech press highlight, hey, performance B is slightly less performance than product A, but it's more energy efficient. Well, not really. Okay, so you made an arbitrary choice. Is this choice meaningful? Again, the answer is no. What I show here is statistics of existing systems. This does not include our new product because they are not shipping yet. 100,000 of platform running in the field, executing real user applications. The light blue is the density of, or the resonancy in minutes that the system spends in each and every frequency bin, and the dark blue is the inverse accumulative, how much time it spends at the frequency and higher. And the left side is the mobile, and the right side is either desktop or mobile working on AC, plugged to the wall. So let's look first on the mobile side. The dot on this shows that the frequency of rated frequency and above, the turbo range, we spend 4 minutes of a day. Let's think a minute. 4 minutes of a day, we stress our CPUs to the maximum, consumes the highest energy, get the highest performance, and the rest of the time we spend in a lower states. Now these 4 minutes are very important. These are the click of the mouse that I show you earlier when we open the file and so on. The desktop side is more aggressive, and it spends 100 minutes out of 11 hours of a day. Still, it is around 10% of the day. And this is probably because we are in the diminishing return range, and we are stressing the part very aggressively. So another view of this of the same statistics. This is the same 100,000 systems, and here what we did is categorize the parts based on the rated TDP. The rated TDP is the out-of-the-box sticker max power that the CPU is designed to, and it is plotted as a function of the average power consumed in the field. So in the last 20 years, I mean, since 2000 when I became a power architect, these TDP values have almost didn't change. I mean, we always have the mainstream notebook was 35 watt notebook, and we always use it. What was changed is that Moore's law and all the advances in architecture and technology allow us to get a richer and more elaborated user experience on our computers. So if we get 35 watt, we use it. We'll have now machine learning and AI. We will see workloads that run these algorithms on the notebook, will do amazing stuff on our application, and they will use the power and energy budget that we have from the system. So if for 20 years we didn't get a change in the energy consumption, that just doing more, then how can we get the improvement in battery life and improvement in carbon footprint? The y-axis shows the picture. The ratio between actual consumed average power over the day compared to the rated TDP, or the point at which we are measuring the energy efficiency. So by implementing the features that I have shown, tracking the user behavior, showing when the user needs it, and giving the full TDP capability, the full energy budget to this application, while keeping the rest of the time at lower energy, this is where we can get the energy efficiency. And as we go forward, this application will show lower and lower ratio between the TDP and the actual average energy consumed over time. So if I summarize, I showed you a set of features and technology that are rolling out in our coming products. The aim of these features is to identify with a set of technologies when the user needs the performance, how much performance. We give all the available energy and deliver great user experience and save the energy the rest of the time. We talked about the matrix. So the matrix that matter are performance and energy at different time scales, performance at the time where the user does something meaningful, and full day energy consumption. Thank you.
Great. I'd like to start with a clarifying question. So when you say performance per watt, is that power of the SoC or power of the complete system, including memory, SSDs, and display?
I'm a SOC architect, so when I measure myself, I measure obviously the SOC energy efficiency. Obviously what matters at the end of the day is the total system.
Okay, Slack.
Yeah, so this question is from Pavan Goti Arm and Cliff Young Google. Do you see ways in which the AI system outperforms previous DVFS control approaches? Is the AI controller somehow better at avoiding false positives and false negatives in classifying high energy use states? And if so, why?
So they are not two separate things. The DVFS is the tool to balance power and power performance or energy performance. The decision of which point to choose, which voltage frequency to choose, is driven by algorithms. We used to do human initiated algorithms. We are adding now the machine algorithms, and the machine learning algorithms show very good capability of predicting what the user does.
So to expand a bit, I think the question was, do you know why this additional AI you've added gets better results than the original human algorithms? I think that's where the question comes.
Yes, I think that I showed it in my example. I showed the Word document open example, and it was able to detect more refined behavior. The human algorithms are looking at narrow window. So we looked at derivative of, going from idle or relative idle to relative busy on one instance, and we don't have the full window of observability. So when we open the full window of observability, we are able to extract patterns.
I don't have any other questions.
Okay, so I'm going to follow up on my question then. So why is optimizing with respect to the SoC's power the right thing to do, since there's a whole lot of other things drawing power? It seemed like the optimal decision would have to consider the whole system.
Consider
the whole system on performance, right?
Yeah. So first, the whole system is highly dependent on the CPU. The CPU itself is a big consumer. The CPU is the one that stresses the memory and other I/O, so they are slaves in this matter, and they are toggled by the CPU. And there are other things which are fixed quality of service. I mean, the screen, the backlight, and other stuff is a tax that is part of the user experience. And there are some things that you can do, and we do, but that's part of the background.
Okay. I see no more questions from the audience. Do we have any more from Slack? Looks like we're thinking of one.
Yeah, this is from Christoph Novak. Will this AI power management algorithm recognize different users? Say a laptop is used by two family members with very different usage patterns. Could that lower the benefit of AI power management?
So currently, it would be fixed. It is trained offline, and it does only inference at runtime. Allowing it to learn on the fly is taking a risk, because it may start behaving weirdly or unexpectedly as we go. Especially it is critical in the corporate market, where you ship to a big customer, and all of a sudden all your acceptance tests and criteria will go wild. It is not. It is possible to have different trained model for different markets. I mean, gaming may be different than consumer, than corporate, and so on.
Thank you.
Okay, last call for Slack questions.
There's one more, I can just read it out. There is this is from Prakash Prabhakar. There is a cooling solution property that it can only cool a certain amount of heat per second. How does that interact with measuring average power across the entire day?
So we make use of the ability of, or the fact that the heat sinks have some heat capacity. So when responsiveness is needed, we often go beyond the TDP capability. We burst higher and we deliver even higher performance, as long as the sustained energy balances, generated energy and dissipated energy is within the balance. But what I showed here is that this is a case which happens on short period of time, on average for most users. If you are a creator, if you are doing movie renders, if you are heavy Premiere user, you may get longer high power instances. And these are traditional capabilities that we have published in the past. We have the thermal controls, we have the power, the system power, and all of these are part of the common practice that we have.
All right, let's thank the speaker.
Thank you.
All right, the last talk that's between you and your break is Caliptra, an open source root of trust for measurements. The speaker is Bharat Pillilli, who's my colleague at Microsoft, but this hardware is not just from Microsoft, it's from a whole bunch of companies, including some of our esteemed competitors. So stay tuned for why we might do such a thing. Bharat's been at Microsoft for 2 years, including data center power efficiency and data center manageability, and lots of stuff on platform and CPU security. Prior to that, he worked at Intel on server CPU architectures. So, Bharat.
Thank you. Well, I don't see anybody running for the doors, so I think it's a good audience. Whenever we talk about security, the thing that we observed is people who deal with power and performance, they tend to leave. And if you're leaving, I think I'll pretend that you're going to a restroom, so I won't be offended. With that, I would want to start with why do we care about Caliptra and why do we need to talk about security today? So the way one could think about it is today when all our personal, financial, professional information is running at a click of a button or a click of an app remotely somewhere. We have various reasons to not get that exposed. Personal reasons. For example, I don't want my wife to see my happy hour bill, so that could be one reason. But at the end of the day, it is important that we protect the security of the data, the security of, say, some company running an AI model, the output of it. You want to protect it in a safe and secure manner. Now, in order to do that, you have to take a lot of actions associated with it. Now, one of the things that CSP's customers tend to do is when you run a particular application or a gaming, they try to co-locate into a data center that is closer to the place where somebody is living because they want to increase the responsiveness with which they would see that. For example, such a data center could be next to my home or a street away, or it could be across the globe, depending upon the fact of responsiveness as well as the cost runs a data center associated. For example, I could be a user of Microsoft Azure, and I want to run an application or a VM at a cheaper because that fits my business model. That means I have to run it in a country or in a place where I budget accordingly so that I don't spend too much money. Now, in order to build such a data center, or build a rack, you need to have CPUs, GPUs, SmartNICs, SSDs, CPLDs, FPGAs, and TOS switches, everything that you create this data center. Now, how do you take the data center? How do you build it? It's a complex supply chain where all these parts need to come together from different companies. You source them, you deliver them to a remote location maybe with armored trucks, B-52s, motorcycles. You could think of it as an action movie. But then I don't know if I will trust such a security that is delivered with such a way. Which means that we need a cryptographic way of ensuring that the supply chain has worked appropriately, and when we build these data centers and we are building this for customers and consumers like us, we can trust whatever is running on this is secure in nature. Now, I answered the hardware problem, but there is the other aspect of firmware. Now, any SoCs that we are seeing today, and the talks that were given by ARM, Intel, much of this essentially runs firmware internally, and this firmware is extremely powerful. You can control power sources, you can control side channels, you can control the security of what these processors provide to the rest of to the consumers of it. And you would see you have a security vulnerability, the way you fix it is using a firmware. So which means what these SoCs are running in a data center remotely across the globe is important for us to know and understand that it is running securely and safely, and that's the guarantee as CSPs that we need to provide to the consumers, and as consumers we need to ensure that these machines are running securely. With that background, I will start with why Caliptra is needed in this context. Before I start, I want to make sure that I give my partners credit that are across various companies who have worked behind the scenes in putting together this particular technology. I didn't use Microsoft PowerPoint, so I guess I need to go do this. Let's see. There we go. So what is root of trust? The way to think about root of trust is the best analogy that I could think of is a passport. So what are the things that are on a passport? First thing is an identity, which is essentially like what my name is. The measurement, which is essentially the information that the passport carries, like my date of birth, what my nationality is, and the life cycle, which is the expiration of the passport. When does it expire? When is it issued, right? And the ownership associated, which means like if you take a driver's license or a passport, we have our signature on it that shows that belongs to me and me only. And the attestation, and you can think of attestation as if I'm going through a customs officer when I'm, say, traveling across countries or at a port of entry, the passport that is taken, when they run it through the database, the information that exists on this passport is legitimate, and it is verified against a central database to say, yes, this is a legitimate passport, the information on this is legitimate, the picture, the sign, the person is a legitimate person. And that's how we want to see a root of trust as. A root of trust is something that is sitting within the hardware, providing this identity and attestation service to say that this particular part that got manufactured across somewhere in the corner of the world that is running at a particular data center is the right processor that you're expecting to run, and the firmware that is running, which is the information that it's providing, is the right firmware that is running on that particular SoC and the device. Now, this particular sort of the side of it is showing the hardware and mutable firmware from a technical point of view. What it is saying is, if you're running a firmware, you have to run it on some processor per se, and you essentially have a set of components together that form this particular root of trust as it stands. Like fuses, cryptos, SRAM, and we'll talk about this when we get to it. Let me shift to the next one. I'll try this again. No. So from a root of trust point of view, it is not that the industry today doesn't have any security within their SoCs. Many companies spend a significant amount of time to provide secure solutions. The problem is there are many solutions. And the industry is fragmented with that particular solution because, I mean, how certain companies see security and what security solutions they offer are pertinent to the business model that they essentially have. And even with these technologies and a good amount of standardization, there are many deficiencies in this. Like, for example, just because someone wrote a good specification does not mean the implementation of it is secure. Something that has to be done in a hardware could be done in a firmware. Something that has to be done in a firmware for flexibility reasons could be done in the hardware. And the question is, how does that impact CSPs? And how does that impact CSP operations? So before we go to it, and to explain why we need such a solution, that is where what we came up with was, we said, hey, let's provide a solution to the industry that is an open source that is implementing the security primitives in a consistent manner. So that's where Caliptra came into play. Caliptra means in Spanish, it's the root tip of your heart, because you need something that sits within the SoCs, that provides the identity, that provides what is this particular CPU, like your passport, what is the identity of the CPU, what is it running. That's where we created this Caliptra. Now, there were two primary goals for Caliptra. One is consistency, the other is transparency. I will actually go through these two particular things in a much more detail in the next slide. So let me skip on to that. Why is consistency important, right? So let's see these two pictures right here, right? So the way CSPs operate, if you think from a platform point of view, one particular component, one particular node, or one rack could essentially contain many nodes, like let's say I have one rack, and within the rack I will have multiple blades, and on each blade I may essentially carry 20 to 40 different components on that particular rack. And SSDs, many of the SSDs I could have on there. I will have to have a SmartNIC to talk to the rest of the world. I'll have CPU to do general compute. I'll have GPUs to do some acceleration. I'll have FPGAs for folks to deploy whatever workload that they want to run, because that's a more efficient way for them to do. The DIMMs today have firmware on them. CPLDs that control how the rack would behave, or how a particular blade will behave. Now, all these entities today contain firmware, and from a customer or a tenant experience point of view, when each of these guys are trying to report what they're running, especially thinking from a confidential computing point of view, we provide what we call as a proof of what they're running. Now, this particular proof from an end user point of view, when I say end user, the company that is using the data center point of view, he or she has to interpret the content that is being reported. And if it is not consistent in nature, they are not sure what that information is from their perspective. The second thing that we have to pay attention to is, for all the components that I just mentioned, as I said, I gave many reasons why root of trust is important. Now imagine trying to audit the hardware and the firmware that is running on these CPUs or SoCs, right, across all these nodes to ensure that it is running securely. And when there is a secure vulnerability or a functional improvement that we have to make, how do we essentially deploy this across millions of nodes and times 40 components, right? And that's a problem that we face today in many of the CSP's data centers. So that is where, for us, consistency of the root of trust becomes important, because the operational complexity of having all these different root of trust is next to insane. And as I said, the customer experience of saying this is the stuff that you're observing and here is a standard way of you're seeing it is a thing that is a customer experience too. And a good question to ask is, hey, there are specs available, there are specs published, and people can implement that. And you would be surprised how different everybody interprets the same specification. The other part that we should not forget is the interoperability of these components, right? It's not like I have a SmartNIC and I have a CPU, they don't talk to each other. they talk to them functionally, but there is a lot of behind-the-scenes security aspect of things of how these particular devices are mutually trusted to each other and how they talk. And this interoperability is also another issue that one needs to wonder about. And the third one, as I say, is it's essentially the life cycle of these devices. For example, we may decommission certain data centers, but they still carry certain SSDs, they may carry certain FPGAs that may have like a longer lifespan, and we may want to move them, right, or memory controllers or DIMMs, we may want to move them to a different place because they are completely safe and completely functionally good devices, right? And the reason to do that is not just because CSPs want to save money. If you think from a sustainability point of view, that's the right thing to do. You don't want to throw away the parts that are working versus trying to reuse them and extend the life of them. So which means we need to care about the functional, not just the functional consistency of them, but also to make sure that their life cycle and where they live and how they live securely is appropriately taken care of. The other part of it that we need to care, or we care, is transparency. So root of trust hardware, or even before we go to the hardware, if you think about the crypto libraries that exist today, they're published in the open. It allows a lot more people and their eyes to look, to review, to potentially find ways to attack them and expose the issues and make them better in nature. So it's essentially the same philosophy that we have adopted, saying that as a root of trust component, we should not maintain, we should maintain an obscurity of it. Trying to not expose that doesn't make the solution better. The decision that we have taken is we will create the design, we will expose the design to the rest of the folks. It not only makes sure that the design is good, it also ensures that the consumers of the design, they see the design and they can audit the design and publicly say whatever the issues that exist with it. And specifically, as I was saying, since this is there to ensure whatever components that are running on the CPU or a given SoC, I know I keep saying CPU, but on any SoC on a platform, is going through Caliptra. Think of it as a doorway through which everything is being executed. I should say the execution is a wrong term, but it's the one that is collecting the measurements of what is running, and it can legitimately say this information that this particular CPU and the firmwares that are running on it is essentially are the things that you're expecting to run. And this would also ensure for us to make sure that the audit aspect of it, like when I have all these N devices, I don't have to audit N root of trust. We can essentially audit one root of trust, and we know that particular root of trust is accurate. Now this brings I'll predict a question that there will be a question saying that, hey, if you're running the same entity, if you have a vulnerability, you will have the same issue. It's a completely legitimate question, but if you think about it from a data center point of view, as a consumer of it, just because I have the best CPU or a GPU doesn't keep my data secure. My data would be flowing over a SmartNIC. My data is kept in an SSD. My data is sitting in the memory controller's DRAMs, right? My data is everywhere. I want everything to be protected. Just because I have a best in class of anything doesn't make my problem go away. And that's where, if I have a consistent solution, if I have a vulnerability of a hardware or a firmware, as a CSP and as a consumer of this data center, I could be more confident on whatever is going to be applied to pass that vulnerability or pass the issue will be uniformly applied, and these issues don't show up at random times. Now I'll get into a little more technical details of Caliptra. I got a couple more slides, but here, with respect to this, what we did was we essentially had a digital logic internal to the Caliptra, and anything that you see in purple here is analog stuff that we want a particular given process to plug and play into it. The other thing that we did was we separated instruction and data ramps so that there is no execution from the ICCM or right back into this ICCM. We ensured that any of these peripherals that sit in here will not be able to DMA into these locations at all. There were quite a few attacks when there is a DMA access that comes with additional complexity. We wanted to eliminate that complexity because the purpose of life of this particular processor is not to resolve the world hunger. Its purpose in life is very specific on what it's supposed to do. The other thing we also ensured is from a SoC interface point of view, since we are trying to plug and play into the rest of the ecosystem, we wanted to implement this as a device, which means that it cannot master random transactions onto the fabric, and consumers of this particular thing from an IP point of view, they can be sure that this whatever firmware that is running on it is not extracting anything from those SoCs themselves. I will talk about side channel protection in the next slide, but the key thing is we don't require any integrated peripherals in this first generation, and that's why it is grayed out. Cryptos and operations. It's a busy slide. The slide is slightly chopped off, but I'll talk about it. From what we implement is DICE is a device identity composite engine. This is something that TCG, Trusted Computing Group, has provided as a solution to the rest of the ecosystem to say, how do you essentially build a root of trust and identity? And what we ensure is we ensure that we implement this fully in hardware without any firmware involvement, which means even if there is a compromised firmware, it cannot spoof an identity of a given device. We kept the fuses externally, but the fuses that are all the security critical fuses, they're essentially decrypted with an internal class key that is specific to each company's SoC, individual SoC. From a cryptos point of view, we have a long list of them that are implemented for the existing thing. We do have PQC support through LMSs, but we'll talk about it later. But for the current generation of products, whatever the NIST standards are, we have implemented those particular things for whatever its purpose in life is. From a key vault and PCI vault point of view, we have ensured that the keys are protected, which means firmware cannot see what the keys are. The keys are completely derived in hardware. Firmware has key handles, and in addition to it, we have attributes to these keys to say how these particular keys can be used going forward. As in, if it's for ECC only, you can only use for ECC. Even PCRs, platform configuration registers that capture the measurement and the information, firmware cannot write to it. You can only extend them, saying that I cannot randomly spoof, I'm running something, but I'm not running it. And we implement the PCR signing, which is a critical nature to say this is the stuff that we are doing, like for attestation, to be completely hardware driven itself. So with that, I'll have last two slides that I think I can cover pretty fast, so that we have more time for Q&A. From the status point of view, we have open sourced this particular content, the first like a 0.5 version of it in last year. The first version of it, the Gen 1 1.0 version, the design part of it is being released as we speak. We built this particular one with a bunch of industry standards and best in practice from different companies, essentially saying, hey, let's do this. This is the practice you need to follow. We have accounted for those, and we ensure that we follow these best practices whenever we are building them. I do want to acknowledge Google, AMD, NVIDIA, and for being the founding partners and providing active help with respect to this. And as I said, and I was just saying that we are in the process of releasing the 1.0 design this week. So what is the next steps? From a next steps point of view, we have an open forum that happens every Friday, 9 a.m. It's a public forum where many companies have been participating for a while. folks who are interested, you can join the forum because there is nothing private about it. You still need to sign a CLA because if you are contributing to it, there should not be any patent associated with it. It's a CHIPS Alliance and OCP rule. So that's what it is. I will end this presentation by saying two things. As best technologies form when we share the ideas together and when people get an opportunity to see what it contains. So if you want to contribute, please come by. Please attend the public work group. Everything is open. The design is open. The specs are open. Feel free to provide your feedback to it. And as I was saying before, security is a critical pillar, and Caliptra is the tip of it. With that, I'll take any questions.
While people are going up to the microphones, I'll ask a question. So you guys got together to do a shared thing here. Like, why now? Why didn't we do this before?
Say that again, Mark.
So in this case, this is a cooperation of a number of companies, including competitors. Why did we get together now and didn't do it before? Is there something that's changed?
Yeah, there is a history associated with it. Microsoft's customers were asking for a transparent root of trust solution, and Microsoft worked with different vendors saying, "Hey, can you do a solution that I'm providing?" And Google said the same, right? And everybody has a similar problem. And if the end vendors account for each company's solutions to be integrated, their die and the silicon area and everything will be humongous. And there is saying a particular SoC is a Microsoft versus a Google versus Amazon may not be the right choice, or is not the right choice from the vendor's point of view. That's where, in all appreciation to the rest of the partners, everybody came together and said, hey, how about we essentially have one implementation that we could use, open source, and all of us either buy the implementation of it and integrate that into the thing to satisfy everybody's needs.
Matt Ashcraft, NVIDIA. So with open source security software, you can review the code, you can compile it yourself and make sure that you have a clean instantiation of it and know that there's no backdoors or whatever. With something that is presumably baked into a third-party ASIC, how do you, as a CSV, do that review to make sure that somebody didn't put a backdoor into their chip?
That's a great question. That is a question that we've been asking ourselves every day. Unfortunate thing is, so I'll give two answers: non-technical answer and technical answer. The non-technical answer of it is tied to a legality of it. If I'm a SoC vendor who's building a SoC, and if I'm taking Caliptra and I'm calling it a Caliptra, I put a backdoor in, and somebody else takes a Caliptra and they don't put a backdoor, and you have vulnerability, you will go through a CV analysis of it. And when you go through the analysis, if that is identified that somebody put a backdoor associated with it, right? It's a risk that you don't want to take. Now, that's a legal aspect of it. From a technical point of view, something that we've been working with some foundries is how do we essentially create a hardware watermark? And we don't have a solution to, I don't have a solution right now to say this is what the thing is, but we've been trying to figure that thing out.
So that's a work in progress, basically?
That is a work in progress.
And if you have a solution, talk to them afterward.
Yeah, please.
Okay.
Hi, Rob Egan, Synopsys. I had a related question to the last one. So because the Caliptra is a peripheral, it means it does, as you said, it doesn't speak until it's spoken to. So there's some sort of time period between when the device is powered on and when anything anywhere can talk to that peripheral. How is security managed?
It's a great question. So the way you can think of data center is, unlike a mobile laptop that we bring up and we start operating, from a data center point of view, when a particular node comes online, node as in a rack or a blade comes online, we don't let it talk to the external world directly. What we do is we first verify, we attest that whatever this particular device and devices are on this particular platform are the legitimate devices that we care about, and only then we allow it to connect to the external world that can send any other packets to it. So to answer your question, because we do the attestation, and without attestation we don't connect to it, it is not necessary that that said, it's not like we are running illegitimate firmware. You do verification, authentication of the firmware, but is that what we are running is something that we verify through attestation at a data center level.
All right, thanks.
Slack.
Yeah, two questions. First one is from Pete Foley. How is Caliptra better than TPM, and why is it a needed replacement? That's the first question. And second question from Reza, UC Berkeley. Are there hardware or firmware mechanisms to attest a region of memory before execution of the code in that region?
Yeah. If I don't answer something, please repeat. So TPM is a discrete component typically. You can have firmware TPMs that are running, but TPM is not necessarily a root of trust. TPM is something that you use once the platform essentially boots. But here we are talking about the very first code that runs on a CPU, and anything that runs on the CPU until TPM comes into play. Even if TPM is completely wiped out, root of trust still remains. The second part of the question was, do we do execution of it? Can you repeat that?
Are there hardware or firmware mechanisms to attest a region of memory before the code execution?
Yeah, so any code that we run into Caliptra or load into Caliptra, specifically from a Caliptra point of view, until it passes the authentication, you do not take it, it doesn't even get to the ICCM from which it executes. So from a Caliptra point of view, that's the obvious answer. If the question is about the SoC firmware, it does essentially the same as we get the measurement of it. The firmware itself is authenticated before it gets onto the SoC. But as I was answering another gentleman, whatever it may run, we don't expect. We check at a data center level. What we expect to see on that particular platform is what we expect to see. It's not previous version or the older version firmware. It is what we expect to see is something that we guarantee through this attestation service.
Okay, final succinct question and succinct answer.
Phil Levis, Google and Stanford. Why no update? Why only measure? Why no update? Why only measurement?
Oh, why no update? Update of the firmware? Oh yeah, we do. I did not talk about the whole seamless update aspect of it, but we do provide update of the Caliptra firmware itself, and we have a model of taking runtime measurements and reporting that from an attestation point of view.
Okay, the Caliptra specification says not update. Right?
It should have a section on seamless update specifically. Maybe it's an older version, but definitely a 0.8 version should have a seamless update associated with it. We wouldn't do something that is not seamlessly updatable.
So before we thank the speaker, I just want to point out it's a break now, and you should come back at 4:45 for the next session on CPU. So let's thank Bharat and all the speakers.